For a long time we have clung to a simple conviction that to find life we must find a twin of the Earth. A rocky planet, a familiar blue sky and a brilliant golden sun. But the universe, in its vast and mischievous nature, seems to be whispering that we have been looking in the wrong direction. In 2023, a signal emerged that shattered every expectation held by the astronomical community. It wasn't a photograph of lush green forests or the glimmer of distant cities, but rather a single, staggering number: 99.7%. On a planet drifting 120 light-years away, the James Webb Space Telescope detected the very breath of life within an architecture that humans once deemed uninhabitable. A world with no solid ground, besieged by crushing pressure and a shroud of hydrogen gas. We once believed we understood the boundaries of life, but K2-18b is proving that our understanding was merely a scattered fragment of a much grander design. As always, I'd love to know where in the world you're listening from and what time it is where you are. And don't forget to subscribe to Space Lull so you don't miss the latest videos. To catch those fragile particles of light that have travelled for 120 years, humanity had to create an environment of extreme stillness. James Webb cannot operate near Earth. Close to our home, it would be blinded by the heat radiating from the Earth, the Moon, and the Sun. And so, scientists sent it to a lonely sanctuary, the Lagrange point L2. 1.5 million kilometers from Earth, L2 is a unique gravitational pocket, a place where James Webb can remain fixed relative to us as we journey around the Sun. Here, James Webb is more than just a telescope. It is a solitary soul dwelling in eternal shadow. To detect the faint chemical whispers from K2-18b, the telescope must exist in a state that physics calls absolute zero. Visualize, if you will, a massive sunshield the size of a tennis court, 5 layers of membrane, thin as a blade of grass, yet incredibly resilient. This shield stands as a barricade between James Webb and the fury of the Sun. On the side facing our star, temperatures can soar to 110 degrees Celsius, hot enough to boil water. But step across those 5 thin layers into the darkness where the gold-plated mirrors hide, and the temperature plummets to -233 degrees Celsius. This is one of the coldest places in the universe ever touched by human hands. Why is this cold so vital? Because James Webb views the universe through infrared eyes. Anything with heat glows in infrared. If the telescope were to warm up even slightly, its own heat would drown out the feeble signals from distant stars. It would be like trying to spot a flickering candle 10 kilometers away while holding a blazing torch right in front of your eyes. James Webb must freeze itself just to hear the whispers of the cosmos. The 18 hexagonal gold-plated mirrors of James Webb unfold like a flower in the dark. Gold was chosen because it is the ultimate reflector of infrared light. These mirrors are so sensitive that they could detect the heat of a single bumblebee on the surface of the Moon, even if we were standing here on Earth. And it is this very sensitivity that allows James Webb to perform a technique known as transmission spectroscopy. Imagine K2-18b as a tiny grain of sand passing in front of a giant high-pressure lamp, its host star. Each time the planet crosses our line of sight, it doesn't just block a fraction of the light, it allows a sliver of starlight to filter through its atmosphere. As that light pierces through the thick hydrogen clouds of K2-18b, the gas molecules there bite away specific wavelengths of light. In these moments, James Webb does not take a photograph in the way we understand it. Instead, it unravels that light into bands of colour, an infrared rainbow. Scientists at Cambridge gaze into that rainbow, searching for missing black lines. Those lines are the barcodes of atoms. A black line at this wavelength means water, another at that position means methane. The silence at L2 is the price we must pay to hear the language of molecules. In that absolute solitude, James Webb has picked up a signal that, by all rights, shouldn't exist on a world so far from our own. A signal that begins with a sulfur compound and ends with a staggering hope for the existence of another life. When the first spectral bands from K2-18b were transmitted back from L2, the control room at the University of Cambridge fell into a heavy, breathless silence. On the computer screens, Undulating curves representing the intensity of infrared light began to take shape. The scientists were all too familiar with the signatures of methane and carbon dioxide, the common guests in the atmospheres of distant worlds. But this time, at a very specific point on the chart, a strange dip appeared. It sat at a wavelength where most computer models had predicted nothing but a flat, empty line. That dip was the unmistakable fingerprint of dimethyl sulfide, or DMS. To understand why DMS is such a slap in the face to modern astronomical theories, we must turn our eyes away from the telescope and look down at the oceans of Earth. DMS is not an alien compound. If you have ever stood by the sea in the early morning, breathing in that sharp, briny and distinctive scent of the ocean, you are encountering DMS. It is the very breath of the sea. On our planet, DMS is not born from volcanic eruptions or the shifting of limestone. It is a byproduct of the metabolism of phytoplankton, marine algae, and microscopic organisms. When these tiny creatures perish or are decomposed by bacteria, they release DMS into the air. It then rises, interacting with sunlight to create aerosols that help seed the clouds. In other words, DMS is the vital link connecting life beneath the waves to the weather in the sky. For decades, biochemists have scoured for an abiotic path, a way to create DMS without life. They simulated lightning striking methane gas. They bombarded sulfur minerals with intense ultraviolet light. But the results were always the same, practically zero. The inorganic universe simply does not know how to craft DMS. This molecule requires enzymatic processes so complex and sophisticated that only the machinery of a living cell can operate them. Thus, when James Webb detected DMS in the atmosphere of K2-18b with a confidence level of 99.7%, the scientific community was plunged into a state of both exhilaration and dread. In the language of statistics, 99.7% is known as the 3 sigma level. It means the probability that this signal is just a random equipment glitch or stellar interference is incredibly low, only about 0.3%. To reach this level of certainty, James Webb had to observe the planet through multiple transits, gathering billions of photons and running them through thousands of noise-filtering models. The DMS signal did not vanish. It repeated itself, persistent, sharp, and clear. But why is 99.7% such a frightening number? The fear stems from the sheer scale of the signal. On Earth, the concentration of DMS in the atmosphere is extremely low, measured in parts per billion. But the trace Webb found on K2-18b suggests a concentration thousands of times higher, at the level of parts per million. This creates a massive cognitive dissonance. If this signal truly comes from life, then the ocean of K2-18b isn't just habitable. It must be a gargantuan biological soup, where an unimaginable density of microbes is working with an intensity tens of thousands of times greater than all of Earth's oceans combined. Imagine walking through a desolate desert where, according to every law of nature, there should not be a single drop of water or a soul in sight. Then suddenly, you catch the overpowering scent of freshly roasted coffee. Not a faint whiff, but a smell so thick it's as if you were standing inside a massive roasting plant. You see no building, you see no people, but that scent is an undeniable chemical proof. You begin to doubt yourself. Is the smell real, or is your mind hallucinating? Or worse, is there some unknown law of physics in this desert that can create the smell of coffee without a single coffee bean? That is exactly how scientists feel right now. If 99.7% is correct, we must accept one of two earth-shattering truths. Either we have found a planet so teeming with life it is breathless, a world where biology completely dominates geology, or we have just discovered a massive hole in our understanding of cosmic chemistry, some inorganic process that can forge the breath of life in a way we never imagined. The presence of DMS on a planet 120 light-years away is a direct challenge to human exceptionalism. If a tiny molecule, containing sulfur and carbon, can exist there, it means the laws of life are not a privilege reserved for Earth. Life is a pre-installed code in the very fabric of matter, simply waiting for the right conditions to execute. However, Before we can declare K2-18b an oceanic paradise, we must face a brutal reality regarding its size and composition. This is not the small, rocky planet we once thought it was. For decades, as humanity looked up at the stars, we carried a burning desire to find a rocky planet, a world with a solid surface, continents we could set foot upon, and shallow oceans where we could swim. We called these Earth analogues. However, the universe does not operate according to our preferences. When James Webb turned its golden gaze toward K2-18b, it sent back a planetary anatomy that caused every prejudice about life to crumble. K2-18b exists in a strange gap in astronomy. It is roughly 2.6 times larger than Earth and 8.6 times more massive. In our own solar system, no planet of this size exists. We have only small rocky planets like Earth, or gas and ice giants like Neptune and Jupiter. K2-18b sits right in the middle. It is a sub-Neptune. In 2021, before James Webb even launched, Professor Niku Madhusudan from Cambridge predicted a new class of planet he called Hycean. The name is more than just a chemical label, it is a revolution in perception. It is a portmanteau of hydrogen and ocean. K2-18b is the ultimate ambassador for this theory. It has no dry land. It has no tectonic plates or majestic mountains. It is a colossal sphere of water, cocooned within a thick, suffocating envelope of hydrogen gas. Imagine trying to land on K2-18b. You would never find a place to touch down your craft. Instead, you would have to dive. First, you would descend through a gargantuan hydrogen atmosphere, which accounts for 1% of the planet's total mass. For comparison, Earth's atmosphere makes up less than 1/1,000,000th of our planet's mass. The sky of K2-18b is not just air, it is a massive pressure cooker. As you go deeper, this hydrogen gas becomes so dense it begins to take on the properties of a liquid. There is no clear boundary between the sky and the sea. You would find yourself submerged in a strange fog where the pressure crushes any ordinary metal structure. Beneath this atmosphere lies a global ocean, hundreds, even thousands of kilometers deep. These are not the 11-kilometer depths of the Mariana Trench. This is an ocean that occupies the vast majority of the planet's volume. This Hycean architecture changes the entire game for life. We once thought a hydrogen atmosphere was toxic, but in reality, hydrogen is an extraordinary thermal blanket. It allows a planet far from its host star to keep its water in a liquid state. On K2-18b, even though its host star is a faint red dwarf, this hydrogen blanket keeps the ocean temperature at roughly 49 degrees Celsius, a perfect number for biochemical reactions. However, there is a terrifying physical barrier at the very bottom. Because the planet's gravity is so immense, at depths of hundreds of kilometers, the water is compressed so tightly that it cannot exist as a liquid or a vapor. There, the pressure transforms water into hot ice, ice 7. This is a bizarre state of matter that we can only recreate in labs using diamond anvil presses. It is as solid as rock with a crystalline structure, yet it glows red hot from the heat radiating from the planet's core. Life on K2-18b, if it exists, would never know the concept of Earth. These beings live in a perfect three-dimensional space, drifting in a liquid ocean sandwiched between a stifling atmosphere above and glowing hot ice below. They live in an environment where hydrogen, not oxygen, provides the spark for energy. This leads to a profound shift in realization. If K2-18b harbours life, it proves that Earth is not the universe's only gold standard. Earth is, in fact, a rare, rocky oasis in a galaxy teeming with colossal water worlds. Hycean planets might actually be the most common homes for life in the Milky Way. They have larger surface areas, more abundant water supplies, and longer periods of stability than our own planet. We have spent centuries searching for a neighbour exactly like ourselves. But perhaps the first neighbour we find will be a creature of water and hydrogen, living in a world where we could never set foot without being crushed into dust. K2-18b does not ask us to visit. It asks us to expand our minds, to understand that life can write symphonies using instruments we never even imagined. But if this planet truly is a vast ocean world, why is its atmosphere so unstable? Why do scientists call it a chaotic sky? In planetary science, there is an unchangeable law. A dead world is a balanced world. Imagine a room locked tight for millions of years. Over time, every grain of dust will settle, the temperature will become uniform, and the chemical reactions between gases will cease once they reach their most stable state. This is chemical equilibrium. When astronomers look at the atmospheres of Mars or Venus, they see this very stillness. These are skies that have gone to sleep, where every reaction finished eons ago, leaving behind a quiet and predictable mixture of gases. But when James Webb turned its lens toward K2-18b, it did not find that silence. Instead, it witnessed an organized chaos that scientists call chemical disequilibrium. The atmosphere of K2-18b is like a room where someone is constantly stirring up the dust, turning on the heater, and cracking open a window. Spectral data reveals the simultaneous presence of methane, CH4, and carbon dioxide, CO2, in massive concentrations, while carbon monoxide, CO, is mysteriously absent. According to the laws of thermodynamics, on a hydrogen-rich planet like K2-18b, these molecules should have reacted with one another to return to a state of balance. Methane should be destroyed by ultraviolet light from the host star, and CO2 should have been converted into other compounds. The fact that they coexist, maintaining stable concentrations across multiple observations, has only one explanation. There must be an engine of some kind, constantly pumping in methane and absorbing other gases, defying the natural tendencies of chemistry. On Earth, that engine is the biosphere. Our own atmosphere is a magnificent paradox. We have 21% oxygen and a small amount of methane. Chemically speaking, oxygen and methane are sworn enemies. They should react to create CO2 and water. If life on Earth were to vanish completely today, within just a few thousand years, oxygen and methane would annihilate each other, and our sky would fall into a deathly equilibrium. The only reason Earth maintains this imbalance is because plants constantly pump oxygen in, and microbes constantly release methane out. So, when James Webb detected a similar imbalance on K2-18b, scientists realized they were looking at the breath of a planet, a world actively resisting entropy, resisting the rest of matter. This chemical chaos is the fingerprint of a global-scale energy metabolism. However, what makes this paradox even more profound is the sheer concentration of these gases. Methane on K2-18b makes up 1% of the atmosphere, a staggering figure compared to the 0.00018% on Earth. If this amount of methane truly comes from biology, then the activity level of the organisms on K2-18b must be terrifyingly intense. It suggests an ocean that is not just habitable, but an ocean teeming with life. Try to imagine the significance of this for our own perception. We used to view life as something fragile, a thin, delicate film clinging to the surface of a planet, easily snuffed out by the slightest environmental shift. But K2-18b shows us a different script. Life can be a mighty geological and atmospheric force. It doesn't just adapt to its environment, it possesses the environment, commanding the chemical makeup of a planet twice the size of Earth to serve its own survival. James Webb is not just measuring gases, it is measuring the will of matter when it becomes life. This disequilibrium is an affirmation that life is not a glitch in the physical system, but a higher state of matter, one capable of bending the ordinary laws of chemistry to carve out a space for itself. Yet, in this chaotic symphony, there is a missing note. A note that should be clearly present in a hydrogen-rich atmosphere, but one that James Webb absolutely failed to find. That is the strange absence of ammonia. Why would such a simple molecule vanish completely? This is not a measurement error. It is a vital clue leading us to another secret hidden deep beneath the clouds. A true liquid ocean, where life might be eating the very atmosphere itself. Next, we will investigate the case of the missing ammonia, indirect yet crucial evidence confirming that K2-18b is truly a water world, and perhaps a world hungry for nitrogen. In the chemical symphony captured by James Webb from K2-18b, there are loud, resonant sounds like methane and carbon dioxide. But it was a sudden rest, a total silence, that left scientists stunned. According to every physical and chemical model of sub-Neptune planets with hydrogen-rich atmospheres, there is one molecule that should have appeared with absolute clarity, dominant and unmistakable: ammonia, NH3. Ammonia is a simple compound made of one nitrogen atom and 3 hydrogen atoms. In an environment saturated with hydrogen gas like K2-18b, nitrogen, a common element in the universe, should easily bond with hydrogen to form ammonia. This is a fundamental law of pressure chemistry. On Jupiter or Saturn, ammonia is everywhere, creating their signature clouds. But on K2-18b, James Webb scanned the entire spectrum, and the result was a flat 0. Not a single trace of ammonia was found above the equipment's noise threshold. This absence is not a measurement error, it is a deliberate emptiness of nature. And to scientists, this void is one of the most powerful pieces of evidence supporting the existence of a gargantuan liquid water ocean. Why is that? The answer lies in the chemical personality of ammonia. It is incredibly fond of water. Ammonia is one of the most water-soluble gases known to man. If K2-18b were merely a dry, gaseous planet like Neptune, ammonia would linger in the air, and James Webb would see it easily. But if beneath that hydrogen atmosphere lies a vast liquid ocean, that ocean would act like a giant sponge. It would suck the ammonia right out of the sky, dissolving it into the deep waters and imprisoning it there. The disappearance of ammonia is the indirect key, confirming that K2-18b doesn't just have clouds and haze, it truly has a liquid surface. This is a massive turning point in our understanding. We cannot look through the thick clouds to see the waves of the sea, but we see an atmosphere washed clean of ammonia, and that can only happen if a colossal volume of liquid water is in direct contact with the sky. But the story doesn't end with physical dissolution. There is another, bolder hypothesis, one steeped in biology. Life is hungry for nitrogen. On Earth, nitrogen is the liquid gold of life. Every DNA molecule, every protein structure requires nitrogen to form. However, atmospheric nitrogen, N2, is incredibly difficult to break apart. Therefore, organisms usually prioritize ammonia, a much more digestible form of nitrogen. If the ocean of K2-18b is truly teeming with life, as the DMS signal suggests, then these creatures would need a massive amount of nitrogen to sustain their dense populations. They might be actively harvesting ammonia from the atmosphere, converting it into living matter, leaving the sky empty of nitrogen. Imagine a giant city viewed from above. You don't see the people, but you see the trash being cleared, energy being consumed, and food disappearing from the shelves systematically. The shortage of resources is the proof of the consumer's existence. On K2-18b, ammonia is that missing food source. This paradox creates a majestic picture of the interaction between life and its planet. Here, life is not just a guest residing on the surface, it is a part of the global chemical cycle. It commands the structure of the sky by draining the ammonia and pumping back dimethyl sulfide. It is a closed loop, a biological engine so powerful that it changes the look of a planet from hundreds of trillions of kilometers away. The data on the absence of ammonia forced scientists to abandon the hypothesis of a cold gas planet. It placed K2-18b on the list of water worlds, the most essential prerequisite for life as we know it. However, having liquid water is not enough. For life to exist and thrive steadily over billions of years, the planet needs something else: temperature stability. Yet K2-18b has an unusual orbit. It moves in a flattened ellipse, causing the distance between it and its host star to change constantly. This leads us to our next mystery. How can life endure the brutal heat pulses every 33 days? In the next part, we will explore the elliptical orbit and the pulse of survival. where life proves its extraordinary ability to adapt in the face of devastating heat waves. On Earth, we are fortunate to live on a planet with an orbit that is nearly a perfect circle. The distance between Earth and the Sun varies only slightly, maintaining a stable temperature throughout the year and allowing biological cycles to unfold in a rhythmic harmony. But K2-18b does not possess that luxury. When astronomers measured its movement around its red dwarf star, they discovered a staggering figure. Its orbital eccentricity is 0.2. To visualize this, the orbit of K2-18b is a flattened ellipse. This means that in its brief year of only 33 days, the planet constantly plunges toward its host star, only to be flung back into the deep cold. At periastron, the closest point, K2-18b receives 50% more thermal radiation than it does at apoastron, the farthest point. Imagine the severity of this. Once every 2 weeks, the entire planet undergoes a devastating heatwave, where the hydrogen sky blazes and the ocean heats up violently. Then, just 2 weeks later, temperatures plummet as the planet drifts into the freezing outer reaches. This is not the slow change of seasons we know on Earth. This is a thermal pulse occurring at a breakneck speed. The question arises, how can life, an entity so exquisitely sensitive to temperature, survive in such a cosmic microwave? The answer lies in 2 factors: the protective power of the atmosphere and the miracle of microbial adaptation. First, the gargantuan hydrogen atmosphere of K2-18b acts as a thermal damper. With a thickness of thousands of kilometers, it possesses immense thermal inertia. As the planet hurtles toward its star, this atmospheric layer absorbs much of the excess energy, preventing the ocean temperature below from rising too abruptly. And as the planet moves away, it radiates the stored heat, keeping the ocean from freezing solid. The hydrogen atmosphere is more than just air to breathe. It is a global climate control system, softening the thermal shocks of the host star into gentler breaths at the ocean's surface. Yet, even with this protection, the temperature flux remains a life or death challenge. This is where the pulse of survival begins. On Earth, we are familiar with extremophiles, bacteria that thrive in boiling geysers or endure within permafrost. But on K2-18b, life may have evolved to do both simultaneously within a single short cycle. Astrobiologists hypothesize that microbes in a Haitian ocean might operate through a hibernation and bloom mechanism. When the planet is at its farthest, coldest point, cells might transition into resilient spores, halting all metabolism to preserve energy. And the moment the planet plunges back into the warmth of the star, a biological explosion occurs. The entire ocean awakens in unison, performing photosynthesis and reproduction at lightning speed to capitalize on the abundant energy. This bloom could explain why the concentration of dimethyl sulfide, DMS, is so staggeringly high. It is possible that James Webb happened to observe K2-18b exactly when it was nearest to its star, the moment when the oceanic ecosystem was at the peak of its activity, venting billions of tons of DMS into the hydrogen sky. Survival on K2-18b is not about stillness. It is a rhythmic dance choreographed to the planet's orbit. Life there does not fear change, it harnesses it. It turns heat waves into an engine for growth, and freezing silences into a time for rest. The symphony of life on K2-18b is written in the notes of extremity. It shows us that life does not need a perfect environment to begin. It only needs a cyclically stable one to learn how to adapt. But this thermal pulse is only half of the story. While the elliptical orbit creates a violent temperature pulse for the entire planet every 33 days, another geographical feature of K2-18b creates a spatial divide that is even more severe: tidal locking. Due to its close proximity to its host star, the immense gravitational grip of the red dwarf has seized K2-18b, forcing its rotation to sync perfectly with its orbit. As a result, the planet always shows only one face to its sun, much like the moon always shows only one face to the Earth. This creates an extreme polarization. On the day side, a fierce red sun stands frozen at the zenith, baking the ocean and atmosphere relentlessly for billions of years. On the night side, darkness is eternal, so cold that gases can condense into snow. Between these two opposing hells lies a narrow ribbon encircling the planet, where the boundary between light and shadow meets. Scientists call this the terminator zone. Imagine standing in the heart of this zone. The star K2-18 never rises higher into the sky, nor does it ever set. It sits motionless right at the horizon, massive and deep red, like a giant dying ember. Here, the light exists in a state of eternal copper twilight. The thick hydrogen atmosphere scatters the red light from the host star, creating hues of bruised purple, aged bronze, and amber vibrant yet somber. This is the only place on the planet where the temperature is neither too hot to boil the water away, nor too cold to freeze the ocean solid. This is the sanctuary of stability. The terminator zone is more than just a quiet strip of water. It is the heart of the global circulatory system on K2-18b. Driven by the massive temperature difference between the two sides, powerful hydrogen winds howl from the heat to the cold in the upper atmosphere, while colossal oceanic currents carry warm water from the day side to the night side to balance the thermal energy. The terminator zone is where these currents converge. Here, life may find its most ideal environment, undisturbed by the 33-day orbital pulse. While microbes on the day side struggle with UV radiation and heat waves, those in the terminator zone live in a nearly constant temperature. They do not need to evolve complex hibernation mechanisms. They can harness the steady infrared energy from the star sitting on the horizon to perform a unique kind of photosynthesis. On Earth, plants crave the blue and red light of our sun, but on K2-18b, the red dwarf emits most of its energy as infrared. If there are phytoplankton in this twilight zone, they likely would not be green. They would be jet black or deep violet, evolved to absorb every last faint infrared photon. These black biological carpets could cover the ocean surface for thousands of kilometers along the terminator, creating a majestic and haunting spectacle beneath a copper sky. It is within this stable zone that biological reactions occur most continuously and resiliently. This is likely the primary factory for dimethyl sulfide, DMS. Because the terminator zone offers the perfect blend of warmth and upwelling currents carrying nutrients from the deep, the density of life here could reach its peak. As these microbes perish, DMS is released and swept away by global winds, dispersing throughout the planet's atmosphere to eventually be caught by James Webb from 120 light-years away. The terminator zone of K2-18b is a testament to the universe's ingenuity. Even in the most extreme environments, nature always leaves a narrow doorway for life. It reminds us that habitability does not need to cover an entire planet. Sometimes, all it takes is a sliver of stability, sandwiched between two infernos, to start the symphony of biology. But as stable as this twilight zone may be, it is still influenced by what lies beneath. Under the liquid waters of this eternal sunset, the ocean of K2-18b is unimaginably deep. And as we dive further, beyond where the light can reach, we face a physical reality even stranger than the hydrogen sky. A place where water is squeezed so tightly it turns into a solid, even while remaining scorching hot. On Earth, we define liquid water as the symbol of life, and ice as the symbol of stagnation and cold. We are accustomed to ice forming only when temperatures drop below 0 degrees Celsius. But in the deep heart of K2-18b, this rule is shattered by an iron fist: pressure. Imagine diving into the ocean of K2-18b. At a depth of 10 kilometers, the pressure is already enough to crush the steel hulls of the most modern submarines. At 50 kilometers, the weight of the water column above is equivalent to placing the entire Everest mountain range on an area the size of your palm. But the ocean of K2-18b does not stop there. It continues down for hundreds of kilometers. In these profound depths, water molecules are packed so tightly together that they can no longer slide freely like an ordinary liquid. They are forced to rearrange into a solid crystalline structure. The result is a bizarre physical entity that scientists call Ice 7, or more popularly in astronomical terms, hot ice. The name hot ice may sound like a linguistic paradox, but it is a precise physical reality. In laboratories, by using diamond anvils to create massive pressure, humans have proven that water can solidify at temperatures of hundreds or even thousands of degrees Celsius if the pressure is high enough. On K2-18b, this ice layer is not cold at all. It absorbs heat radiating up from the planet's core, causing it to glow red like a block of coal. It is as hard as rock, yet it possesses the chemical essence of water. The presence of this hot ice layer creates a geological boundary of vital importance for the possibility of life. On Earth, the liquid ocean is in direct contact with the rocky silicate crust. This interaction allows minerals, metals, and nutrients from the ground to dissolve into the water, providing food for the very first biochemical reactions, what we call hydrothermal vents. But on K2-18b, the liquid ocean above may be completely sealed off from the rocky core below by a layer of hot ice thousands of kilometers thick. This separation poses an existential question for the DMS signal found by James Webb. If the ocean is cut off from the mineral source at the rocky core, where does life get the nutrients to bloom so intensely that it alters the entire atmosphere? This is when we must reconsider the dynamism of this hot ice. It is not a static block of stone. At extreme pressures, hot ice can behave like a plastic material. It moves, it convects, and it transports heat as well as chemical compounds from deep within the planet upward through cracks and slow convective flows. This ice layer acts as a filter, a gargantuan membrane purifying chemicals before they enter the liquid ocean. Furthermore, the existence of hot ice at the bottom helps maintain the stability of the ocean above. It acts like a massive pressure cooker, keeping the water in a stable liquid state despite the terrifying temperature fluctuations from the host star outside. Hot ice is the solid foundation of the Hycean world. It is what prevents the ocean from either evaporating completely into space or collapsing entirely into the core. For a creature living on K2-18b, this hot ice layer is their ground, even though that ground may lie hundreds of miles below the surface and be hot enough to melt metal. Life here likely did not begin in rocky crevices as it did on Earth, but rather at the fragile boundaries where liquid water meets the glowing, heat-radiating crystals of hot ice. This layered structure, hydrogen gas, liquid ocean, and hot ice, creates a biological machine on a scale far beyond our understanding. It is a perfect arrangement of physics to protect life from the harshness of the universe. K2-18b does not need to be like Earth to be habitable. It has created its own version of habitability, where extreme pressure is not the enemy, but the great protector, keeping liquid water alive for billions of years. The patience of liquid water on K2-18b is guaranteed by the resilience of this hot ice, and that resilience, in turn, is warmed by the oldest and slowest father in the universe, the red dwarf star K2-18. In the next part, we will look up at the sky to admire this eternal space heater and understand why the lifespan of the host star is the deciding factor that allows life on K2-18b to far surpass life on Earth in both complexity and longevity. In the human collective consciousness, a life-giving star must be a brilliant golden orb, as radiant and warm as our sun. We consider the sun our gold standard, the ultimate symbol of life. But through the lens of modern cosmology, our sun is actually a rather hurried and short-lived star. It burns through its fuel wastefully and will reach the end of its life in about 10 billion years. In contrast, the host star of K2-18b belongs to an entirely different class, the red dwarf, M dwarf. Red dwarfs are the most common stars in the Milky Way, making up nearly 70% of all stars. They are smaller, cooler, and emit far less light than our sun. If the sun is a roaring campfire, the red dwarf K2-18 is merely a glowing ember, smouldering steadily. Yet it is this very smouldering that is the greatest gift the universe bestows upon life on K2-18b. It is the gift of absolute time. The principle of a star is simple. The larger it is, the higher the pressure at its core, the faster it burns hydrogen, and the sooner it dies. The red dwarf K2-18 is so small that the pressure at its core is just enough to sustain nuclear fusion. It conserves fuel to an extreme degree. While our Sun will exhaust its hydrogen and swell into a red giant, incinerating the Earth in 5 billion years, K2-18 can continue to burn steadily for hundreds of billions, even trillions of years. Pause for a moment to absorb that figure. The current age of the universe is only 13.8 billion years. This means that when our Sun has long since gone dark, and the Earth is nothing more than a frozen rock drifting in the void, K2-18 will still be shining, still warming the hydrogen atmosphere of K2-18b. This is no ordinary heater, it is an eternal one. For life, time is the most crucial ingredient for building complexity. On Earth, life took 4 billion years to journey from the first simple cells to brains capable of thought. We have used nearly half of the Sun's lifespan just to reach our current level of complexity. We are racing against the clock. But on K2-18b, life does not need to hurry. If life there began at the same time as on Earth, it has had an absolutely stable environment in which to evolve, and it will have hundreds of billions of years more to continue experimenting, failing, and perfecting. However, red dwarfs also have a violent, dark side, especially in their youth. These stars frequently emit incredibly powerful X-ray and ultraviolet stellar flares that can strip away the atmosphere of any nearby planet. This was once the reason many scientists doubted the possibility of life around red dwarfs. But James Webb has provided vetoing evidence. K2-18b has held onto its thick, hydrogen-rich atmosphere. This means either the planet possesses a super strong protective magnetic field, or K2-18 has entered a quiet, gentle middle age. The current stillness of K2-18 is a perfect condition for long-term stability. Without erratic tantrums from its star, life beneath the Hycean Ocean can establish biological cycles that last for millions of years without interruption. While Earth constantly endures climate shifts due to solar cycles or orbital variations, K2-18b may be enjoying an era of peace longer than anything humanity can imagine. The red light from K2-18 also shapes the very nature of life here. Since most of the radiation is infrared, the hydrogen atmosphere filters out high-energy rays and traps thermal energy. Organisms on K2-18b will never know the blinding glare of golden sunlight. Theirs is a world of hazy warmth, where sight might not be the most important sense, or if it is, their eyes would evolve to see heat instead of colour. The patience of the red dwarf teaches us a lesson about existence. We often judge a system's success by its brilliance and scale, but the universe prioritizes endurance. The worlds around red dwarfs might actually be the seed banks of life in the galaxy. When great stars explode and become black holes, tiny heaters like K2-18 will still be silently keeping the biological flame alive. James Webb's discovery of DMS on K2-18b didn't just find a molecule, it found a biological system that has potentially existed with more stability than Earth for far longer. Life there could be older, deeper, and more grounded than us, because they have a father who never hurries, a star that has promised to warm them until the very end of time. But no matter how patient a star is, scientific data demands absolute rigour. Why does 99.7% still keep scientists awake at night? Why haven't we officially popped the champagne? In the next part, we enter the world of statistics and the battle of the sigmas, where human caution duels the desperate longing to find a kindred spirit in the cosmos. In everyday language, when someone says they are 99.7% sure of something, we consider it an absolute. It is a level of trust that is almost impossible to shake. But in the cathedral of physics and astronomy, 99.7%, known as the 3 sigma level, is a number that is both haunting and indecisive. It is like standing before a door that is cracked open, yet you still do not have the right to walk through. To understand why scientists at Cambridge and NASA are painfully cautious when announcing data about K2-18b, we must understand the gold standard of all discovery, the 5 sigma level. In statistics, a 3 sigma level means there is a 1 in 370 chance that the dimethyl sulfide, DMS, signal is just a random coincidence of equipment noise. That sounds very safe. But remember that James Webb is gathering billions upon billions of bytes of data. In such a vast sea of information, it is entirely possible for a random error to appear at a rate of 1 in 370. In the history of science, there have been many times when brilliant 3 sigma signals vanished into mist as more data was collected. 5 sigma is different. It represents a confidence level of 99.99994%. At this level, the chance of error drops to 1 in 3.5 million. This is the standard physicists at CERN used to announce the discovery of the Higgs boson in 2012. It is the standard for confirming the existence of gravitational waves. For a claim as world-altering as life found beyond Earth, science accepts nothing less than 5 sigma. Because the price of a false announcement is too high. Look at the painful lessons of the past. In 1996, the world was shaken when NASA announced evidence of fossilized bacteria in the Martian meteorite ALH 84001. Even President Bill Clinton gave a televised speech on the event. But just a few years later, independent studies showed those structures could have formed entirely through abiotic geological processes. The initial excitement turned into a decade-long disappointment, eroding public trust in astrobiology. Or more recently, in 2020, with the discovery of phosphine gas on Venus. The signal was strong, suggesting life in the acid clouds. But as other research teams joined in, they discovered it might have been a data processing error or a confusion with sulfur dioxide. These scars in scientific history have created a culture of extreme caution. Scientists would rather be seen as slow than be seen as wrong on a matter of such monumental importance. The 99.7% figure on K2-18b currently places us in a dramatic state of limbo. James Webb has caught a very clear signal, repeating across multiple transits. The DMS signature appears at the exact wavelength it should. But to push this number from 3 sigma to 5 sigma, we need more time. We need to observe the planet through dozens more transits to completely rule out interference from the host star K2-18-, a red dwarf that can have unpredictable fluctuations in light. The battle of the sigmas is, in truth, a battle between longing and logic. On one hand, the heart of every researcher wants to believe we have found a cosmic peer. DMS is too specific a molecule, too tied to life to be a mere accident. On the other hand, scientific reason forces them to ask the cruelest questions. Is there a mineral on K2-18b we don't know about that could create DMS? Could the hydrogen atmosphere, under UV radiation, produce a strange chemical reaction we haven't yet simulated in a lab on Earth? This very rigour is what protects the truth. If one day the 5 sigma figure appears on the reports for K2-18b, we will know for certain that it is not a mirage. It will be the moment humanity officially enters a new chapter of history. However, while we wait for the statistics to perfect themselves, another group of scientists has issued a chilling warning. They suggest we might be looking at a hell on Earth in clever disguise. This is the magma ocean hypothesis, where DMS is not the breath of life, but the exhaust of a world on fire. In the next part, we face the dark side of the signal to see if James Webb is being deceived by a hellish illusion. Amidst the wave of optimistic reports about a Hycean world brimming with life, a group of researchers in early 2024 poured a cold bucket of water over the international astronomical community with a controversial paper. They hypothesized that James Webb might not be looking at a liquid water ocean at all, but rather a scorched magma ocean. In this scenario, K2-18b is not a cradle for life, but a gargantuan furnace trapped beneath a suffocating hydrogen sky. The argument for this hypothesis is rooted in a brutal thermodynamic calculation. K2-18b is significantly larger than Earth, meaning it had the gravitational strength to retain a massive amount of hydrogen gas from the era of star system formation. Hydrogen is not just light, It is an incredibly effective greenhouse gas when under high pressure. If this hydrogen atmosphere is too thick, accounting for a few % of the planet's mass, it would act as a superpowered thermal flask. Under that hydrogen blanket, the heat from radioactive decay within the planet and the thermal energy left over from its formation cannot escape into space. As a result, surface temperatures could skyrocket to 600 degrees Celsius or even 1000 degrees Celsius. At such heat, no ocean can exist. Every water molecule would be driven upward as steam, and beneath it, the planet's rocky crust would melt completely, forming a global ocean of glowing red lava. So why did James Webb find dimethyl sulfide, DMS, a molecule ostensibly tied only to life? This is where the magma hypothesis becomes chilling. Chemists suggest that in the hellish environment of a magma ocean, complex inorganic chemical reactions could occur. As sulfur compounds erupt from the depths into the scorching hydrogen sky, they could interact with methane under extreme pressure to create sulfur-based organic molecules. James Webb might have detected a fake chemistry, molecules that look like the breath of life, but are actually the exhaust of molten rock. However, the magma hypothesis is not without its flaws, and it is these very cracks that offer hope to the side of life. The key lies in methane, CH4. James Webb recorded methane making up 1% of K2-18b's atmosphere. Chemically, methane is extremely unstable at high temperatures. If the surface were truly a 600 degrees Celsius magma ocean, methane should be destroyed and converted into carbon monoxide, CO, in a very short time. The presence of abundant methane, alongside the total absence of carbon monoxide, is the Achilles heel of the magma hypothesis. For such a high concentration of methane to persist, K2-18b's atmosphere must be much cooler than the magma scenario allows. Or there must be a source of methane so massive it defies logic to compensate for the thermal destruction. The clash between water ocean and magma ocean has turned K2-18b into the greatest intellectual battle of the decade. One side believes in oceanic life based on DMS and methane. The other leans toward fiery geology based on the absence of ammonia and the insulating power of hydrogen. The data from James Webb is like an optical illusion. Look at it one way, and it is a paradise. Look at it another, and it is a hellscape. Yet there is a third possibility, one that neutralizes both extremes and opens a vision even more magnificent. What if K2-18b has a hot surface, but life has found a way to survive in the higher cloud layers where temperatures are mild? Or what if that liquid ocean is not at the surface, but hidden deep beneath high-pressure ice, with life operating a chemical communication system through the layers of matter? The magma debate has taught us a lesson in humility. We cannot take the mindset of a creature living on a rocky surface and impose it upon the entire universe. K2-18b might not be a hell, and it might not be an Earth-like heaven. It might be an intermediate state for which we do not yet have a vocabulary. Leaving behind the flowing lava, we return to the liquid ocean hypothesis to explore an idea even more astonishing. If life is there, it isn't just existing. It might be operating a global communication network, a climate control system that humanity has only just begun to dream of. In the next part, we will explore planetary-scale quorum sensing, where trillions of microorganisms on K2-18b are together, writing the symphony of the sky. On Earth, we often view bacteria and phytoplankton as simple organisms, existing independently and passive to their environment. But modern biology has revealed a different truth. Microbes can communicate. They use a mechanism called quorum sensing. By releasing chemical signal molecules into the environment, bacteria can count the density of the population around them. When the number of individuals reaches a certain threshold, they change their behavior in unison, attacking together, glowing together, or building massive biological structures together. Now, apply this concept to K2-18b-, a world with no dry land, no continents, only a vast liquid ocean connecting one pole to the other. On Earth, microbial communication is fractured by continents, obstructed by ocean currents, and localized by climate shifts. But on K2-18b, the ocean is a perfectly unified system. Every chemical molecule released at one end of the planet can be carried by global currents to the other side. In such an environment, quorum sensing is no longer the story of a cluster of bacteria in a puddle. It becomes a communication network on a global scale. Scientists hypothesize that the staggering concentration of dimethyl sulfide, DMS, detected by James Webb, might be the language of this network. Rather than just an accidental waste product, DMS could be a signal molecule released with intent. Trillions of microorganisms on K2-18b might be together writing a chemical symphony to coordinate the survival of the entire planet. Why would they do this? The answer lies in stability. As we know, K2-18b faces brutal heat waves from its elliptical orbit. To survive, the oceanic ecosystem needs rhythmic coordination. When the density of DMS reaches a certain level, it could trigger simultaneous reactions. Perhaps the creation of aerosols to form thick clouds that shield the ocean from solar radiation at periastron, or, conversely, thinning the clouds to absorb heat as the planet drifts away from its star. If this hypothesis is true, K2-18b is not just a planet that has life. It is a planet that is alive, in the most literal sense. Life here has evolved beyond individual existence to become a force of planetary-scale engineering. DMS is not just a breath. It is the nervous system of a gargantuan biosphere, where the boundary between the individual and the environment is blurred. Try to stand beneath the copper sky of K2-18b and feel this. You do not see creatures with distinct forms. You do not see civilizations built of metal and concrete. Instead, the entire ocean around you is a biological intelligence, a massive water brain, constantly calculating, adjusting chemical levels and temperatures to maintain its own balance over billions of years. The presence of DMS in parts per million thousands of times higher than on Earth is the resounding roar of this collective intelligence. It shows that the biosphere on K2-18b operates with an intensity and cohesion that Earth has never achieved. We often search for alien civilizations through radio waves or macrostructures, but perhaps the universe has created a kind of microbial civilization, an entity built not of brick and stone, but of absolute chemical resonance. K2-18b is teaching us a new definition of evolution. Evolution does not necessarily lead to individuals with separate intelligence like humans. It can lead to a collective harmony where the entire planet becomes a single organism, the Gaia hypothesis. This is the great cognitive decentering that K2-18b brings. We might be the most intelligent species on Earth, but perhaps we are still primitive compared to the absolute chemical unity of our neighbours 120 light-years away. Having faced this oceanic intelligence, we are forced to ask a more fundamental question. What is life? Is it a rare accident, or is it a basic physical law that will appear wherever the conditions are right? In the next part, we enter the deepest existential layer of our journey, the third decentering, where K2-18b teaches us that life is a constant of the universe. As we enter 2026, the planet K2-18b is no longer a distant, obscure target. It has become a priority mission on the agenda of the James Webb Space Telescope. If 2023 was the year of astonishment, and 2024 and 2025 were years of fierce debate, then 2026 is the year of determination. Since the first detection of the dimethyl sulfide, DMS signal, in September 2023, James Webb has been granted dozens of additional observation hours to monitor K2-18b through at least 5 new transits between late 2025 and early 2026. This raw data, after travelling millions of kilometres from the L2 point back to Earth, has been fed into supercomputers for a process scientists call data stacking. By layering the light spectra from multiple transits on top of one another, astronomers have significantly reduced the white noise from the host star, K2-18. The results obtained in mid-2026 are staggering. The DMS signal has not faded as the random noise hypothesis predicted. On the contrary, it has emerged with unprecedented clarity. The absorption lines at the 3.4 micron wavelength are not only deeper, but have begun to reveal satellite lines, tiny chemical details that can only belong to the molecular structure of dimethyl sulfide. But the true turning point of 2026 came from another instrument on James Webb, MIRI, the mid-infrared instrument. While previous observations relied heavily on NIR spec, near-infrared, the mid-infrared observations of 2026 allowed us to look into a frequency range where hydrogen and methane molecules become more transparent. This allowed scientists to peer straight down into the atmospheric layers directly above the surface of K2-18b's ocean. The latest data reveals a startling truth. The concentration of DMS is not evenly distributed across the planet. It is most heavily concentrated near the equator and, specifically, within the narrow ribbon of the terminator zone. This reinforces the hypothesis that DMS is being pumped up from a specific source beneath the water, rather than being created by chemical reactions triggered by ultraviolet light in the upper atmosphere. If this were an abiotic process, it should be strongest where radiation is most intense, but its concentration in stable, warm waters is a biological signature that is becoming increasingly difficult to deny. As of 2026, the statistical confidence of the DMS signal has surpassed the 3 sigma threshold and is narrowing in on 4.2 sigma. In the world of numbers, the distance between 3 and 5 sigma is a gargantuan abyss, yet every 0.1 sigma step forward requires exponential precision. We have not yet reached the gold standard of 5 sigma to officially pop the champagne, but the probability of error has now dropped from 1 in 370 to roughly 1 in 15,000. The confidence of the scientific community is visibly rising. Press releases from the University of Cambridge in 2026 have begun to shift their language. They no longer use the phrase possible signal. They have started using strong cumulative evidence. However, James Webb also discovered a new anomaly in 2026, a slight fluctuation in methane concentration following the planet's 33-day orbital cycle. As K2-18b plunges toward its host star, methane levels surge, then subside as it drifts away. This aligns perfectly with the pulse of survival model we discussed. Life on K2-18b appears to be responding directly and powerfully to the warmth of its sun. This planet does not just have life, it is functioning as a biological entity with a heartbeat synchronized to the cosmos. 2026 is also the year scientists have begun to see the ultimate limits of James Webb. As powerful as it is, Webb is a single telescope. To truly see the final fingerprint, the isotopic fractionation we so desperately crave, humanity will need a combination of Webb's power and a new generation of gargantuan ground-based telescopes. We are standing at the dawn of a new era, where data is steadily replacing dreams. The numbers of 2026 are telling us the story of an oceanic world vibrant with life, 1.1 million billion kilometers away. But to turn 4.2 sigma into 5 sigma, to turn probability into historical fact, we must dive even deeper into the nature of atoms. In the next part, we will explore isotopic fractionation, the atomic detective technique that will help us confirm life through the very weight of atoms, and why this is the final gambit for humanity to officially declare we are not alone. In the hunt for life beyond Earth, finding a molecule like dimethyl sulfide, DMS, is a magnificent achievement, but it is not yet the end of the debate. To bring the world to a 100% confirmation, we need evidence that scientists call the smoking gun. That evidence lies in a subtle phenomenon known as isotopic fractionation. To understand this concept, imagine atoms as balls of the same size, but different weights. Carbon-12 is a light ball, while carbon-13 is slightly heavier because it carries an extra neutron in its nucleus. In the inorganic world, the world of rocks, fire, and random chemical reactions, nature does not discriminate. A volcanic eruption will use carbon-12 and carbon-13 indiscriminately, according to whatever ratio is available in the environment. But life is different. Life is an entity that is incredibly lazy and efficient. Enzymes in living cells when performing photosynthesis or metabolism, always prefer to use lighter isotopes like carbon-12 because they require less energy to break chemical bonds. As a result, any compound created by a living organism, from methane to dimethyl sulfide, will carry an unusually high ratio of carbon-12 compared to its surroundings. This is a chemical fingerprint that cannot be forged. If we can measure that the concentration of light carbon in the methane of K2-18b dominates absolutely over other inorganic sources, it would be the ultimate confirmation that a biological machine is operating beneath those clouds. A magma hell, or high-altitude photochemical reactions, cannot perform this sophisticated atomic selection. However, James Webb, despite being a modern technological marvel, still struggles to separate these fragile isotopic signals from 120 light-years away. Webb's spectral resolution is enough to identify the molecule, but not yet enough to weigh each atom perfectly. That is why, in 2026, the eyes of the scientific world are not just on the L2 point, but also directed toward a towering mountain peak in the Atacama Desert, Chile. Here, the extremely large telescope, ELT, is nearing completion. With a gargantuan mirror 39 meters in diameter, nearly 7 times larger than James Webb, the ELT will be a machine possessed of unprecedented light-gathering power. When we combine the clean infrared data from James Webb with the ultra-high spectral resolution of the ELT on the ground, we will, for the first time, be able to see the difference in the mass of atoms within the atmosphere of K2-18b. The ELT won't just see DMS, it will dissect it. It will tell us if the sulfur in that molecule bears the mark of life. On Earth, sulfur-reducing bacteria perform isotopic fractionation, similar to how plants do with carbon. If a concentration of light sulfur-32 dominates the DMS signal of K2-18b, all doubts of an abiotic origin will be extinguished. Imagine the gravity of that moment. We wouldn't just be saying, there is DMS there. We would be saying, we have weighed every atom, and we see the signature of energy preference, a trait unique to biology. This is the moment science moves from speculation based on presence to affirmation based on behavior. Isotopic fractionation is the final boundary separating us from absolute truth. If James Webb opened the door, then the ELT and isotopic measurements will be the guides leading us through it. It transforms K2-18b from a potential candidate into a validated living laboratory. But as we wait for those final isotopic numbers, we stumble upon another terrifying silence. If life on K2-18b is developing so powerfully that it alters an entire atmosphere, and if Hycean worlds like this are common in the universe, why haven't we heard a radio greeting yet? Why can the ocean of K2-18b be teeming with life, but remain desperately silent to the eavesdropping projects of SETI? If the 99.7% signal from K2-18b is real, and if Hycean planets truly account for 40% of the worlds around red dwarfs, then our Milky Way should be a gargantuan botanical garden. With tens of billions of vast oceanic worlds, the universe should not be silent. Yet for over 60 years, the SETI project, Search for Extraterrestrial Intelligence, has pointed massive radar dishes into the void and received nothing but the soulless static of background radiation. Why do we find the breath of life, DMS, but not the voice of technology? K2-18b may hold the answer to the Fermi paradox through a brutal reality that scientists call the ocean prison. Consider the structure of K2-18b once more. It is a world with no land. A global ocean hundreds of kilometers deep covers every square meter of its surface. For microbial life, or even complex multicellular organisms, this is a paradise. Water is the perfect solvent. It protects life from radiation and provides an infinite three-dimensional space to evolve. But for the construction of a technological civilization, the ocean is an impassable wall. To develop technology as humans have, you need two fundamental things that K2-18b completely lacks: fire and metal. Fire is the engine of all progress. Without fire, you cannot forge metal. Without metal, you cannot create electrical wiring, you cannot build engines, and you certainly cannot construct radar dishes or spacecraft. On an ocean planet, fire cannot exist. Even if the creatures beneath the K2-18b ocean possessed intelligence far surpassing humans, they could never strike a spark to melt iron ore. They are imprisoned in a perpetual biological era where every tool must be made of bone, shell, or organic polymers. Furthermore, the atmosphere of K2-18b is a terrifying physical barrier. With dense hydrogen gas and extreme pressure, launching any object to escape a gravity 2.5 times stronger than Earth's is a near impossible energy equation. A creature on K2-18b looking up at their copper sky might see the stars, but to them, those lights are forever out of reach. They are locked within a cocoon of water and gas, with no way to send a signal out. This is the paradox of liquid water. Water is what creates life, but too much water is what suffocates technology. The universe may be full of breathing worlds like K2-18b, but they are all silent worlds. We can smell them through DMS, but we will never hear their radio. The silence of SETI all this time may not be because life is rare. On the contrary, life may be common, but technical intelligence like ours requires an incredibly specific and rare geological arrangement. The perfect balance between land and sea. We need land to create fire, and we need water to sustain life. Earth is a singular stroke of luck to possess both. Looking at K2-18b, we realize a new kind of loneliness. Not the loneliness of being the only living thing, but the loneliness of being the only one who can speak, standing in a crowd of neighbours, silenced by their own homes. K2-18b is not just a planet to study, it is a lesson in the freedom of perception. It reminds humanity that we are lucky not only to be alive, but also to be able to see. We have the ability to escape our atmosphere, look back at our planet, and send messages across millions of light years. K2-18b may be older, more stable, and richer in life than Earth, but they will likely never know that we are watching them. When we place K2-18b on the scales against Earth, the planet begins to emerge as a reflection in a mirror. It shows us not only what we lack, but also what we are recklessly gambling away. Explorations of K2-18b are often hailed by the media as finding an Earth 2.0. But after everything we have analysed, it is clear that K2-18b is not a twin, but a haunting antithesis. If Earth is a dynamic, volatile and hurried stage, then K2-18b is like a cathedral of patience. And it is this very difference that transforms a planet 120 light-years away into a mirror reflecting the future of humanity. Look at the chemical stability of K2-18b. The pungent signal of dimethyl sulfide, DMS, and the persistently maintained atmospheric disequilibrium suggest a biosphere that has reached a state of absolute maturity. On that planet, life does not merely exist, it has become part of a global regulatory machine over billions of years. It has survived the flares of its red dwarf, adapted to a brutal elliptical orbit, and lived in harmony with a suffocating hydrogen sky. Meanwhile, looking back at Earth, we see a completely opposite picture. We are the only species intelligent enough to build the James Webb, keen enough to read the fingerprint of DMS from trillions of kilometers away. Yet we are the very species directly damaging the breath of our own planet. In less than 2 centuries, a mere blink compared to the lifespan of the star K2-18, we have altered CO2 concentrations faster than any natural geological process in millions of years. K2-18b is sending us a quiet message. The greatest life is not the most brilliant life, but the most enduring one. That water world teaches us that life is a process of self-regulation. The biosphere of K2-18b has tamed its planet. It uses chemistry to create clouds, uses the ocean to store heat, and uses time to perfect its balance. It does not seek to conquer or exploit, it simply blends into the laws of physics to exist forever beneath the red light of its host star. The 99.7% awe we feel for K2-18b is, in truth, an unconscious admiration for a world that has solved the problem we are currently stuck on, the problem of sustainable existence. We yearn to find them, Not to learn how to fly into space, but to learn how a biosphere can last for trillions of years without destroying itself. The presence of DMS on K2-18b also decenters the human ego. We once thought that if we disappeared, the universe would lose its meaning. But K2-18b shows that the symphony of life is still being played grandly, everywhere, under different suns, in different chemical languages. The universe does not need us to be alive. It was alive long before the Wright brothers left the ground, and it will remain alive long after our sun has faded. Ending this archaeology of light, we realize that K2-18b is not the destination of a journey, but the beginning of a shift in mindset. We are no longer solitary observers standing outside the frame. We are part of a gargantuan biological network, breathing in the darkness of space. Every photon carrying the secret of DMS has travelled for 120 years just to tell us one thing. You are not alone, but you are not the most special either. You are just one note in an infinite song. And your only mission, much like those silent microbes in the Hycean Ocean, is to ensure that the song is not broken on your own planet. Now, as James Webb continues to tirelessly scan the hydrogen clouds of K2-18b, let us take a deep breath of Earth's air. Feel the scent of the sea, of the damp earth after rain, the scent of life truly present. Because somewhere, 1.1 million billion kilometers away, something is performing that exact same breath, looking up at their sky and perhaps wondering about us too. We have travelled a long road, from the fragile photons of 1905 to the rigorous sigma numbers of today. Now is the time for all that knowledge to melt into a single feeling, the peace of belonging to the universe. When the lights on the computer screen fade, when the spectral charts are nothing more than memories in a server's hard drive, what remains with us is not the concentration of dimethyl sulfide or methane. What remains is a permanent change in how we look at the night sky. For thousands of years, humanity looked into the dark void between the stars and saw a deathly silence. We built myths, religions, and philosophies just to fill the fear of absolute solitude. We once believed we were a random miracle, a tiny spark trying to fight against the infinite cold of entropy. But today, K2-18b has brought a gift of salvation. The 99.7% figure is not just the reliability of a molecule, it is the reliability of a hope. It tells us that the universe is not a rocky graveyard. It is a breathing entity. It is living, transforming, and waiting patiently everywhere, from deep hydrogen oceans to eternal Terminator horizons. We are living in the most magnificent moment of cognitive history. For the first time, a part of the universe ourselves has crafted a sensory organ sensitive enough to recognize that another part of the universe exists. It is not an invasion, nor a direct contact. It is self-awareness at a distance, a handshake of time and light. K2-18b does not ask us to come there. The distance of 120 light-years is a reminder that each of us has our own cathedral to protect. If those tiny organisms on that water world can keep their planet stable for billions of years under a red dwarf, then we beings who can see the entire galaxy have no reason to fail on our own home, Earth. The sky tonight remains the same, vast and deep. But as you look toward the constellation of Leo, remember that there is a breath there, synchronized with yours. The universe is no longer silent. It is whispering in the language of chemistry, and we have finally learned how to listen. Thank you for traveling this entire journey with Space Lull. If the vibrations from K2-18b have touched your soul, please share your thoughts with us in the comments. A new journey has only just begun, and your companionship is the light that guides our next discoveries.